Have you ever been trying to use a mobile app? Maybe you're transferring money or, scheduling a complex meeting across two different platforms, and your AI assistant, the one that's supposed to be saving you all this time, just completely chokes.
Oh, all the time. It's the definition of brittle execution, isn't it? It feels like it gets the first two steps perfectly,
Right.
and then it hits some, I don't know, unexpected pop-up or a slightly ambiguous instruction, and the whole thing just collapses. It's so frustrating.
It is. It just grinds to a halt. And that fundamental brittleness is the exact problem that MAI-UI, this new foundational graphical user interface agent, was engineered to solve.
And that's what we're talking about today. Those previous generations of assistants, they were highly optimized for, let's call them perfectly scripted scenarios.
Like a lab environment.
Exactly. Environments where the layout never changed, the instructions were always crystal clear. But the real world, the actual GUI you use every day, it's dynamic, it's unpredictable, and it's full of human ambiguity.
And that's what we're digging into. We are doing a deep dive today into MAI-UI. Our source is a recent, and I mean extremely detailed, technical paper. It outlines the whole architecture, the training methods, and critically the state-of-the-art results it's getting across some major industry benchmarks.
What's genuinely exciting here, and I think this is the key takeaway, is that MAI-UI isn't just a small incremental upgrade. It's not just a little bit better.
Cool.
It's a fundamental rethinking of the architecture. It introduces multiple paradigm shifts in how these agents handle things like ambiguity, how they protect your privacy, how they manage these ultra-long multi-step tasks.
And even how they manage resources, which is huge.
It is. And this system is proving it can fundamentally outperform major competitors. We're talking about the big proprietary models that get all the headlines, like Gemini 3 Pro and Seed 1.8, in these key areas of, robust competence.
So our mission today is to break down exactly how MAI-UI was built. What are the specific breakthroughs that allow it to navigate the digital world so much more like a human expert would?
Well, to do that, the agent really needs two things, and it needs to be great at both. First is deep visual grounding.
Which means knowing where on the screen to click, right? The precise location.
The precise pixel. And second is sophisticated navigation, which is knowing what sequence of steps to take. And crucially, that includes knowing when to pause and ask for help, or even when to skip the entire interface by using a system shortcut.
It's moving beyond just being a simple click-and-type bot.
Fundamentally, yes. These UI agents need to move beyond being just simple action execution models. They need true intelligence, an intelligence that's grounded in the visual world. They have to understand complex intent, and maybe most importantly, they have to manage computational resources intelligently. MAI-UI tackles this entire spectrum.
And it really moves us closer to an assistant that actually works consistently.
An assistant you can rely on.
So let's give you a snapshot of just how potent this is, because the numbers here, they really validate the whole approach. MAI-UI, in its largest forms, is setting new state-of-the-art records.
They really are.
On AndroidWorld, which is a major benchmark for online mobile navigation, it achieves a whopping 76.7% success rate.
And let's put that number in perspective. A 76.7% success rate means the assistant is now reliably completing almost 3 out of every 4 complex tasks. These could be financial tasks, multi-app workflows.
Things where the previous generation might have failed half the time or even more.
Exactly. And then if you look at the grounding capability, that visual acuity we talked about on ScreenSpot Pro, which is a benchmark specifically testing GUI grounding on these incredibly dense, high-resolution professional screens.
So not just a simple mobile app.
No, think CAD programs, scientific software. On that, MAI-UI hits 73.5% accuracy, and that's the number that actively surpasses powerful proprietary competitors like Gemini 3 Pro.
So these aren't just minor statistical nudges.
Not at all. These numbers show a foundational shift in reliability. It proves they've really started to solve that underlying brittleness problem.
Okay, let's unpack this. If these previous agents, even the big well-funded ones, were so technologically smart, why were they still falling short when they actually hit the real world?
That's the billion-dollar question, isn't it?
It is. And the MAI-UI paper outlines 4 critical open challenges that they explicitly engineered their system to address. This is what moves it from an academic curiosity to something you could actually deploy securely.
Right. It's a transition from just demonstrating a capability in a controlled, clean environment to handling the absolute chaos of a live operating system where, anything can happen at any time. They really honed in on the four things that always caused catastrophic failure.
So if brittleness is the big umbrella problem, what was the first major friction point the engineers decided to tackle?
The very first thing they realized was that the agent couldn't just blindly follow orders. It had to be able to handle human ambiguity.
The ambiguity problem.
Exactly. They formally call it the agent-user interaction problem.
Tell us more about that. What does that look like in practice?
Well, most current systems are optimized for what's called end-to-end execution. A user gives a simple, perfect instruction, and the agent just executes it until it's done. Or it fails silently.
Which is the worst.
It is. But think about your own daily instructions. How often are they perfect? Imagine telling an agent, find the latest quarterly report and send this to Mike.
Okay.
If you have 3 Mikes in your contacts, Mike Smith from finance, Mike Jones, your neighbor, and Mike Chen from marketing, and you didn't specify which one.
The system has no idea what to do.
It has no choice. It either crashes or, and this is far worse, it makes an assumption and sends potentially sensitive company data to the wrong person.
But isn't training an agent to know when to ask for help much harder than just training it to execute a command? I mean, how do you make sure it doesn't just interrupt the user constantly for every little thing?
That is the core challenge. The requirement isn't just execution, it's what they call proactivity rooted in intent alignment. The agent has to proactively recognize that an instruction is ambiguous or incomplete.
So it has to have a sense of what's missing.
Precisely. And then it has to ask a clarifying question. And to ensure success, it also has to collect those missing details, like which Mike's email, and this is critical, seek explicit consent for operations that involve sensitive data or irreversible actions.
Like sending an email or making a payment.
Exactly. This proactive interaction is a capability that was almost entirely neglected in previous systems. They were just focused on maximizing the raw number of tasks completed end-to-end. But an effective agent needs to interact and clarify, not just blindly follow.
That makes perfect sense. And it leads us right into challenge number 2, moving beyond UI-only actions. The paper calls this the brittleness and reachability problem.
Right. So if an agent's entire worldview is just limited to clicking, typing, and swiping basic UI manipulation, it immediately runs into 2 huge bottlenecks.
And the first one is about error propagation.
Bottleneck number 1 is simply that long, multi-step UI sequences, they increase brittleness exponentially. They just amplify error propagation if you're manually clicking through, say, 30 different screens to accomplish a task.
Which happened.
It does. And if there's a small, unexpected layout shift or a copy-paste error way back in step 5, the entire 30-step task collapses 25 steps later.
It's exactly like a digital Rube Goldberg machine. You're reliant on every single tiny component firing perfectly. And the chances of that happening in a live operating system are basically 0.
Virtually 0. And that brings us to bottleneck number 2, which is that relying only on the UI limits the agent to only those tasks that are UI reachable.
What do you mean by that?
Well, what if you need to manipulate data that's deep inside a system, something that only exposes its functionality through a structured API? Or maybe you need to query some specific metadata that requires a command line interface. A UI-only agent is completely stuck. It's just staring at the screen, unable to complete the task.
This is where the big innovation comes in, integrating external tools via what they call the Model Context Protocol, or MCP.
MCP is the structured shortcut. And this is so vital because it allows the agent to compress those long, fragile, multi-step UI sequences into just 1 or 2 robust API calls.
So instead of clicking through a dozen menus...
Exactly. Instead of clicking links, copying data, scrolling endlessly, the agent can just issue a single MCP call. This drastically reduces the surface area for failure. The source material gives a fantastic illustration of this.
Oh, yeah.
MCP tools unlock tasks that were previously just infeasible on mobile. Things like manipulating GitHub repositories directly from your phone or executing complex file system operations. It brings these traditionally desktop-only workflows to the mobile environment without you having to battle a tiny interface.
That's a huge deal.
Yeah.
Then we hit challenge 3, which is crucial for, mass market adoption and user trust.
Right.
Native device cloud collaboration. This is about solving the privacy and cost problem.
Right. And current GUI agents, they typically fall into one of 2 extremes. They're either lightweight, running entirely on your local device.
Which is great for privacy.
Great for privacy, but very limited in capability because the models have to be small. Or They're these massive, powerful models that can only be used as expensive cloud services.
And the cloud-only solutions are powerful, yes, but they have their own problems.
Huge problems. High serving costs, total dependency on network connectivity, and most critically, they introduce major privacy risks by constantly sending everything, every screenshot, every temporary input, every user action off your device for processing.
So the real requirement is a system that can intelligently get the best of both worlds without forcing you to make those trade-offs.
A truly practical system needs a seamless native device cloud collaboration, an architecture that's designed for privacy-aware, cost-efficient routing, and effortless handoff between the two.
So it needs judgment.
It needs judgment to know when it can handle a simple task locally, saving money and protecting data, and when it absolutely needs to call in the heavy artillery, that big, high-capacity cloud model, to solve a complex or failing step. That intelligence and resource management is key to MAI-UI's efficiency.
And finally, that brings us to Challenge 4, robustness to dynamic environments. This is the real-world unpredictability problem.
This is the nemesis of all digital assistants.
It really is. The sudden, unexpected pop-up notification, the Slate app update that shifts a button by a few pixels, or the permission dialog that just wasn't there in the training data.
Exactly. Agents that are trained exclusively on static, pre-collected trajectory data, which is how most academic agents start, they often overfit.
They just memorize the screenshots.
They essentially memorize the training set. But when you face them with a live, real-world GUI where layouts vary dramatically across app versions, or where an unpredictable element like a new promotional banner suddenly appears, they fail miserably because they haven't learned to generalize.
So the requirement here is training that forces the agent to generalize beyond those static sets.
And critically, to learn how to recover from unpredictability without needing the user to intervene. That's a huge shift, and we'll see later how MAI-UI solved this using massive-scale online reinforcement learning. So here's where it gets really interesting. This is where MAI-UI built its dual foundation. Before an agent can even decide what to do next, that's the navigation task. It must first perfectly understand the current screen and where to act.
The perception and grounding.
Exactly. MAI-UI is built on superior GUI grounding or localization and robust mobile navigation, which is the sequence of actions.
Let's start with that foundational layer then, grounding. For anyone who might be new to this, how is the grounding task technically defined in this context?
It's very precise. You give the model two things, a GI screenshot and a natural language instruction, let's call it I. The agent's job is to predict a precise coordinate point, P, defined as X and Y coordinates.
So the exact pixel.
The exact pixel location of the target UI element that matches the user's intent. It's about finding that specific target on the screen.
And the performance here is what validates the entire system's perceptual capabilities. You mentioned those extremely difficult high-resolution professional layouts earlier. What do the quantitative results show? How good is MAI-UI at this?
The results are extremely strong. They really affirm the quality of their architecture. MAI-UI's highest performers, specifically the 32 billion and 235 billion parameter variants, establish new state-of-the-art performance across 5 well-known grounding benchmarks.
Okay, let's focus on one that really tests its limits. You mentioned ScreenSpot Pro.
Yes, ScreenSpot Pro. This is where the rubber meets the road for complex professional tools.
We're talking about dense enterprise dashboards, CAD systems, scientific applications, that kind of thing.
Exactly, sprawling office layouts. And the reason that benchmark is so much harder than a standard mobile app interface is because the UI is incredibly dense. The critical elements, the buttons, the input fields, the little controls are often fine-grained, tiny, and packed incredibly close together.
So when you compress that high-res screen into a standard input size for the model,
all those tiny details become impossible to distinguish accurately. But MAI-UI tackles this head-on. The MAI-UI 32B model, when it's running at full capability, achieves 73.5% accuracy.
now, that's a big deal.
It's a huge deal. That is an absolute accuracy gain of 4.1% over the strongest comparable baseline. And crucially, this is the score that pushes MAI-UI beyond proprietary competitors like Gemini 3 Pro and Seed 1.8 in the specific, very difficult domain. It proves its effectiveness on the most demanding, visually complex software layouts out there.
And a major component of getting that 73.5% accuracy is their secret weapon, the zoom-in strategy. That sounds critical for making sense of those tiny elements. Can you break down how that two-pass mechanism works?
Absolutely. The core challenge is the fine resolution of the targets on a high-density screen. When a model processes the entire image at once, the tiny details you need for accurate localization are just lost.
To get blurred out.
They get blurred out. So the zoom-in strategy overcomes this through a really intelligent two-step refinement process. In the first pass, the model looks at the entire screenshot and predicts a course coordinate, just a general area on the screen where the target probably is. Think of it like pointing to a neighborhood on a map.
A general target, not a precise one.
Exactly. Then the system intelligently crops a specific smaller window that's centered on that course point. They usually crop a region that's about half the dimensions of the original image.
Oh, okay.
This cropped window is then resized back up to the model's original input resolution, which effectively zooms in and sharpens that specific area. In the second pass, the model refines its prediction based only on this zoomed-in, high-detail view, and that's when it outputs the precise coordinate.
So this iterative refinement is why they see that big jump in accuracy.
Precisely. That's why they see that substantial 5 to 6 point jump, especially on these fine-grained, high-resolution tasks where the targets are just a few pixels wide.
So they turn a blurry general target into a sharp, focused one before making the final call. That makes perfect sense. What about instruction complexity? It's one thing to say click the save button, but what about more abstract, multi-perspective queries?
That's where the UI vision benchmark comes into play. This benchmark specifically tests grounding performance based on the diversity and complexity of the natural language instruction.
So it's not just click button, it's more nuanced.
Way more nuanced. Instructions can be complex, involving spatial references like the button below the profile image, or functional intent like the control to finalize the payment, or even abstract reasoning. And MAI-UI shines here too.
What are the numbers?
The 32B model achieves 49.2% accuracy with the zoom-in strategy. Now, that number might sound lower, but it's a massive jump of 12.4 percentage points over the previous best model.
12 points is huge in this space.
It's a gigantic leap, and it confirms MAI-UI's superior ability to understand these multi-perspective, abstract, or high-level instructions. It proves it can handle the nuance of real human language.
We've seen other results cited too. On MMBench GI L2, which involves following hierarchical instructions and compositional reasoning, MAI-UI hits 91.3%. What's telling there is that the improvement is largest on the advanced instructions versus the simple basic ones.
Which again confirms its ability to grasp these implicit high-level commands. And all of this superior grounding performance, it points directly back to a highly effective training methodology.
The instruction is reasoning paradigm.
That's the one. It's a two-stage process. Supervised fine-tuning, or SFT, followed by reinforcement learning, RL, using a specific algorithm.
Explain that SFT stage for us. How do they literally inject instructions as explicit analytical reasoning into the model? That sounds fascinating.
It is. The SFT stage is where they teach conceptual understanding and stability. They teach the model to use diverse instruction perspectives. They define 4 core types: appearance, what it looks like; location, where it is; functionality, what it does; and intent, what the user wants to achieve.
Okay.
They teach the model to use these as explicit analytical reasoning before it ever predicts the coordinates.
So instead of thinking, instruction says, save, click, save button, the model is forced to think something more like, the instruction is functional, save, now I need to find the element on screen with the functionality save. Okay, that's it. Location X, Y, now I click.
Exactly that. This structured reasoning is explicitly trained into the model, and they found that injecting this analytical step is what stabilizes the later, more volatile reinforcement learning phase. It actively prevents what researchers call policy collapse, which is where the agent's behavior degrades rapidly during self-exploration.
And then the reinforcement learning stage comes in to refine that reasoning, to make it adaptive.
Precisely. The RL stage uses a reward system to incentivize the model to dynamically select the most appropriate reasoning perspective based on the actual context it encounters on the screen.
So if the instruction is purely spatial, like click the top left button,
the model learns to prioritize the location reasoning path. If the instruction is vague, like finish this job, it might prioritize intent and functionality. They use a straightforward but really effective reward scheme. A format reward, which just checks if the thinking and the coordinates are structured correctly, and a point-in-box reward, which gives a direct yes-no signal for correctness.
Simple but effective.
Very. And this entire grounding foundation is what makes the model so adept at finding the right pixel, even in these complex, abstract situations.
So what does all this superior grounding actually mean for you, the end user? It means the assistant can see and pinpoint tiny targets on a professional spreadsheet or a CAD program, and it can understand complex, multi-layered instructions.
Right. And now we can shift to how it navigates the entire mobile ecosystem. This is where MAI-UI moves beyond just clicking pixels and really starts handling ambiguity and using shortcuts.
And the true test for this is the mobile world benchmark.
It's the crucible. MAI-UI adopts this specifically because it's the new gold standard for realism. It's not just single app tests. MoWorld covers over 201 realistic, complex tasks across 20 different applications.
Everything from social media to enterprise tools.
Everything. Social media like Mastodon, enterprise communication like Mattermost, e-commerce platforms like Mall4Uni. And crucially, it mandates comprehensive evaluations for both agent-user interaction and that MCP tool integration we talked about. This is real life.
And on this difficult, real-world benchmark, MAI-UI delivered exceptional results, especially against competitors that were only optimized for that old metric of just end-to-end execution.
It really did. The largest model variant, the 235B, achieved a 41.7% overall success rate on Mobile World. That's a huge margin. It significantly outperforms the strongest end-to-end baseline model by almost 21 percentage points.
21 points is a blowout.
It is, and even when you compare it to these complex agentic frameworks that rely on strong external high-level planners, MAI-UI remains highly competitive as a single, cohesive end-to-end model.
So let's break down the two features that make this realism possible, starting with feature 1.
Yeah.
MCP tool integration, the structured shortcut. How did the engineers technically enable the agent to stop just clicking and start using these system-level shortcuts?
They expanded the agent's action space. Traditionally, the actions were restricted to just GUI actions, click, swipe, type, and so on. They added a new specialized action MCP call.
And that's the key.
That action enables the agent to directly interact with external tools and services defined by the Model Context Protocol. It lets it access structured data and services without ever needing to perform GUI clicks. The agent can essentially bypass the interface when structured data is available.
And the case studies they provide in the paper, they really illustrate the efficiency gain here. Let's look at the route planning example because that perfectly captures a realistic cross-application task that currently drives users insane.
It's a perfect example. Imagine this scenario. The user asks the agent to compare two apartment listings they've found, figure out which one have the shortest driving time to a specific office campus, let's say the Alibaba Jinxie campus, and then email the address of the closer apartment to a colleague named Mia.
Okay, if I had to do that manually, I'd be switching apps like crazy. Opening the map app twice, copying and pasting two addresses over and over, reviewing the results, maybe manually calculating the difference, then composing the email.
Exactly. It's maybe a dozen UI operations, and every single one is prone to copy-paste errors, scrolling failures, mental fatigue. It could easily take 3 minutes of just fiddling with your phone.
For sure.
Instead of that error-prone sequence, the MAI-UI agent recognizes the intent is route comparison, so it uses an AMAP MCP call. It takes the office as the origin, the two apartment addresses as destinations, and it retrieves the structured travel time and distance instantly.
One call.
One clean tool call compresses that fragile multi-step GUI operation into one efficient API interaction. It instantly gets the data it needs.
That dramatically lowers the complexity and the brittleness of the whole sequence. And it really showcases how this expands the agent's actual utility. It moves these desktop-level workflows seamlessly onto your phone.
And consider another task. Retrieving the last 3 commit summaries, the author and the message from a GitHub repository, and emailing it to a team member.
On a desktop, that's easy.
A breeze. A simple command or a well-designed web interface. But on a mobile phone, trying to browse commit history through a mobile browser UI is just cumbersome. The screen is too small, it's slow to load, you're endlessly scrolling through logs.
A nightmare.
By using MCP calls, the agent can bypass that interface entirely. It queries the repository's metadata directly via the protocol, receives the structured commit data, extracts what it needs, formats it concisely, and composes the email. This makes these traditionally complex, desktop-only tasks feasible and efficient on mobile.
That flexibility is key to making the agent indispensable. Now let's move to feature 2, agent-user interaction. This is how they solve that ambiguity problem, training the agent to know when to stop and ask for help.
And once again, they expanded the agent's action space. They added a new action, a scuser.
Simple enough.
The agent is trained to proactively use this action whenever it detects that the instruction is vague, underspecified, or critically missing a necessary parameter. And to achieve this, the training method is revolutionary. They construct tasks with deliberately omitted critical information.
So they're intentionally engineering failure scenarios into the training data. That seems counterintuitive at first.
It does, but it's absolutely essential for teaching clarification. When the agent reaches a step that requires this missing detail, say a specific delivery address or an exact file name or the recipient's email address, it issues an accuser action.
And what happens then? Who answers?
This query is routed to a synthetic user agent. It's just a standard large language model that's been conditioned on the hidden missing context of that specific scenario. The synthetic user provides a concise, context-appropriate reply, and the MAI-UI agent's trajectory then continues, incorporating the new information.
So it forces the model to learn the necessity of clarification rather than just guessing.
Exactly. It can't guess. It has to ask.
The case study for file sharing really grounds this in a common experience.
It really does. Think about this. You ask the agent to locate several resume files in your downloads folder and send them to an HR colleague. MAI-UI begins the task. It finds the files, it opens the compose email screen, but at that point, it detects missing details. The recipient's email address and the desired email body content, the greeting and the subject line.
And instead of guessing or just failing to send,
it pauses execution and issues an accuser action. Please provide the HR colleague's email address and the desired subject line. Once the user provides those details, the agent resumes the GUI trajectory, autofills the email fields, and successfully completes the sensitive task.
The proactive clarification is absolutely essential for handling the noise and incompleteness of real-world human requests.
And the quantitative result confirms it. MAI-UI achieves a 51.1% success rate on the user interaction subset of mobile world. That's beating the previous best end-to-end baselines by almost 19 percentage points. The ability to use tools and interact proactively just makes the whole system exceptionally robust. So if we connect all these pieces to the bigger picture, all these robust features, the deep grounding, the tool use, the human-like interaction, they all require a highly stable and scalable foundation to be reliable in the real world.
And this is where the training and deployment innovations really shine. This is the engine room. This is how they address that brittleness problem head-on through massive scale and intelligent architecture.
It really is.
Let's start with how they achieve that real-world robustness. It sounds like supervised fine-tuning alone just wasn't enough to handle those dynamic environments, the pop-ups and the app updates. That required scalable online reinforcement learning.
That's correct. Online RL is really the only proven method to truly enhance reliability in long horizon tasks and to build robustness against unpredictable environments. But training RL on GUI environments is notoriously difficult.
Why is that?
Because they're stateful and they are incredibly resource intensive. Every single training rollout needs its own isolated running environment. You can't just run a simple simulation. You need a live Android system running for each one.
So what was the technical solution for this environment scaling bottleneck? How did they manage hundreds of live phones running at the same time?
They engineered a comprehensive, containerized, virtualized environment. This basically encapsulates the entire live GUI environment inside a Docker image.
So it's self-contained?
Completely self-contained. Inside that Docker container, they run a rooted Android virtual device, along with self-hosted backend services for the apps they need to interact with, and a dedicated REST API server for external orchestration. This complex setup guarantees consistency across training runs and ensures massive generalizability because they integrated over 35 diverse applications into this framework.
And how did they coordinate the sheer scale needed for effective RL training? I mean, 500 instances sounds like a logistical nightmare.
That's where the centralized environment manager comes in. This manager coordinates all of these container instances across multiple physical server racks. This architecture is capable of supporting up to 512 concurrent environment instances for massive parallel rollout execution.
Wow.
And the manager is smart. It handles efficient resource utilization by reusing containers instead of destroying and recreating them for every task, and it provides fault tolerance to seamlessly replace any instances that fail. This ability to run 512 parallel live GUI experiments is the critical innovation that allowed them to collect enough diverse experience to overcome the data limitations and overfitting of static training.
This level of scale sounds absolutely essential for training long, complex tasks. Speaking of which, they mentioned tasks up to 50 interactive steps. That must create impossibly long streams of data trajectories containing millions of tokens during training. How do they solve the long horizon optimization problem without just running out of memory on every GPU?
That's the second major technical feat they solved in the engine room. These ultra-long trajectories, we're talking millions of tokens of screen captures, actions, observations, they simply exceed the memory capacity of any single GPU.
It's just too much data.
Way too much. So they address this with a strict on-policy asynchronous RL training framework, which utilizes two critical parallelism techniques.
First, tell us about asynchronous rollout. Why does that speed things up so much?
Well, traditional synchronous pipelines are incredibly slow because the powerful GPU, the expensive part, sits idle, waiting for the relatively slow environment interactions to complete.
The clicks, the app loading.
Exactly, the swiping. Their custom agent loop asynchronously dispatches requests to specialized inference servers. This means the GPU isn't sitting around waiting for the Android simulator to catch up. It constantly has data to process. This mitigates GPU idling and significantly accelerates the generation efficiency.
And second, hybrid parallelism. This is the part that gets highly technical. TP, PP, and CP tensor, pipeline and context parallelism. We need an analogy here. How do they shard a multi-million token trajectory?
Okay, think of that multi-million token trajectory like tearing a massive multi-volume novel into tiny pieces. No single person or GPU can read the entire thing efficiently. To process it fast, you need specialized readers. Tensor parallelism, TP, is like splitting single massive sentences, the large tensor representation of the data across multiple workers. Pipeline parallelism, PP, is like splitting the book into chapters, sending chapter 1 to one GPU, chapter 2 to the next, and processing them in an assembly line.
So the data moves through the system sequentially, but each piece is processed by a dedicated stage.
Precisely. And context parallelism, CP, is the most important one here for length. It allows them to break up that ultra-long context, the millions of tokens, into smaller, manageable blocks. They leverage all three dimensions of this parallelism to shard the entire ultra-long rollout trajectory across multiple GPUs.
And that's how they could train on these massive 50-step tasks.
That is how they enabled scalable end-to-end training while keeping the memory usage on any single GPU bounded and manageable. This engineering efficiency also let them realize that using 720p resolution instead of 1080p gave them a huge 50% speedup per step without compromising performance.
And the RL works. It provides measurable gains across all model sizes, which confirms that this massive investment in infrastructure was absolutely worthwhile.
It was entirely necessary. The RL training stage consistently improved the SFT performance. For instance, the MAI-UI 8B model improved by a solid 6.0 percentage points, jumping from a 64.7% success rate to 70.7% on AndroidWorld. The research also showed that training with fewer parallel environments led to performance saturation.
So scaling up to 512 instances was absolutely vital.
Vital for generating enough exploration diversity and achieving continuous policy improvement.
And this enhanced robustness, it shows up clearly in the case studies, right? Like recovering from an unexpected pop-up.
Yes, absolutely. The RL-trained model demonstrates superior recovery from these truly unpredictable events. When, for instance, the agent is directed to create a new contact, it might encounter an unexpected notification permission request pop-up that simply wasn't in the static training data.
The SFT-only model would fail there.
It often fails entirely. But the RL-trained MAI-UI successfully identifies it, dismisses the dialogue, and then continues the task without deviation because it has learned the generalized policy of error recovery.
And it can even correct its own mistakes.
It can. During a complex expense management task, the agent might initially navigate to the wrong application, but the RL-trained model can detect that trajectory error and successfully course-correct in the following steps. This proactive robustness is the key difference between an academic prototype and a deployable product.
Okay, let's pivot now to deployment. They recognized that neither a purely local, lightweight agent nor a purely large cloud agent met real-world needs for cost and privacy. The solution was the Native Device Cloud Collaboration, or DCC system.
This is a really pioneering approach for privacy and cost management and AI agent deployment. The system has three main parts. A lightweight local GUI agent, which is the 2B model, a high-capacity cloud GUI agent, the 32B or 235B, and a local unified trajectory memory, which just records everything the agent does and sees.
And the local agent has a dual role here. It's not just the primary agent, it's also an intelligent monitor.
Exactly. The local agent executes the task steps, and critically, it monitors the trajectory for any signs of failure. It checks for common task deviations, An action failing, the agent repeating the same action over and over without progress, incorrect inputs, or just a general task stall.
And if it detects a deviation?
If a deviation is detected and the current screen context is not privacy sensitive, it triggers a switch to the high-capacity cloud agent. It calls for backup.
That brings up the critical innovation here, the error summary impact. When it switches to the cloud, it doesn't just hand over the screen, it hands over an explanation. It's like sending the patient's medical chart to the specialist.
That analogy is perfect. The local agent monitor generates a concise error summary explaining why the local agent failed or deviated. Something like, failure detected, repeated action on next button 5 times, potential layout mismatch.
And that's crucial for trajectory recovery.
It's crucial because the massive cloud agent needs to understand the point of failure to correctly execute the next steps. If the cloud agent only gets the screenshot, it has to start guessing. And their ablation studies showed that providing this error summary yields a significant 6.9 percentage point increase in success rate compared to switching without it. That diagnosis saves the cloud specialist critical time and resources.
What were the efficiency and performance gains of this intelligent DCC system overall?
The combined system is highly efficient. By only relying on the cloud when it's necessary, the DCC system reduces cloud model calls by over 40% compared to a cloud-only solution.
That's a huge cost saving.
A substantial saving in both cost and latency. Furthermore, it managed to complete 40.5% of tasks entirely on device, confirming that it successfully eliminates all those unnecessary expensive cloud calls. And overall, the system improves on-device performance by 33.4% over a local-only model.
So it's better and cheaper.
Exactly. It demonstrates strong performance under realistic constraints while being mindful of your wallet and your data security.
And that security is paramount.